I'd like to explain in this video the pressure enthalpy diagram for a single component system, and then specifically use a diagram for water to talk about some details. So what I'm showing here is pressure versus enthalpy. Notice this is the log of the pressure so that we can really see all the details on the diagram, and enthalpy in kilojoules per kilogram. So the red point, this is the critical point, and that's an important part of the diagram. And so what we want to do, let's look at first some isotherms to get an idea of how enthalpy depends on pressure at constant temperature. So if we look at 100 degrees C and we look over here at the line, which is liquid, so this is liquid, we know the enthalpy is essentially independent to a reasonable approximation. Very high pressures, we see some slight increase, but liquids are incompressible, and therefore, not surprising, their properties don't change much with pressure. Now we go from liquid, saturated liquid, so this line along here is the saturated liquid line. And we go to saturated vapor. Of course, a big change in enthalpy due to the heat of vaporization. And now for the gas at 100 degrees C, the enthalpy is pretty much independent of temperature, and this is behaving very much like an ideal gas because we're at relatively low pressures, 100 kilopascals and lower. If we go to 200 C, it's a very similar behavior. However, at 300 C, things are different. So the liquid phase shows behavior that's essentially enthalpy doesn't depend on pressure significantly. We have the phase change at 300 degrees C, but notice now that as we lower the pressure at constant temperature at 300 C, so going along this line, as we lower the pressure, the enthalpy increases. Or the other way, of course, is that at constant temperature, as we raise the pressure, we actually decrease the enthalpy. So down here at the low pressures, again, it's behaving like an ideal gas. Enthalpy is independent of pressure. But at the higher pressures, and of course these are pretty high pressures, 2 megapascals is 20 bar pressure, and we go from 2 megapascals up to about, say, 8 megapascals, there's a significant change in enthalpy. If we look now at an isotherm that's in the supercritical region, namely above the critical point, so let's look at the 400 degrees C isotherm. Low pressure, ideal gas. But notice now, there's no phase change, but enthalpy, certainly at 400 degrees C, shows a rather large change in enthalpy with a change in pressure as we go, for example, from 10 megapascals up to maybe 35 megapascals, a very large really change in the enthalpy for this supercritical fluid. So enthalpy certainly depends on pressure in addition depending on temperature. Let's look at a couple other aspects of this diagram. These green lines, for example, this line labeled 30% corresponds to 30% quality. In other words, this corresponds to 30% of the water is present as vapor, 70% as liquid at each of the different temperatures and corresponding pressures. Other thing we want to look at is this saturated line. Notice as I increase the pressure, the enthalpy increases for a liquid at saturation conditions because the temperature is also increasing. To stay on the saturated line, pressure and temperature both increase. Stay on the saturated line at a higher temperature, I have a higher saturation pressure, and therefore the enthalpy increases. In contrast, if I look at the saturated vapor line, this line over here, saturated vapor, notice that the enthalpy is almost independent of pressure, even though the temperature is changing. So we're changing the temperature. We go from 100 to 200 C. And of course, if we went from 100 to 200 C at constant pressure, there'd clearly be a change in enthalpy that would be significant. But going from 100 to 200 C while increasing the pressure, we see almost no change in enthalpy. So very slight dependence when we have both pressure and temperature changing saturated vapor. The final thing I like to use this diagram to show is, and one of the reasons that this is a useful diagram is if we look at, say, a throttle process. So if we start with the saturated liquid and we throttle it, namely an adiabatic process, flow process, enthalpy doesn't change, so delta H equals 0 for a throttle process, adiabatic, then that means if we started with a saturated liquid and we lowered the pressure, we'd end up with a vapor-liquid mixture, and we would drop the temperature significantly by throttling and lowering the pressure. And of course, this is what we take advantage of in a refrigeration system. By dropping the pressure through a throttle, we get a large temperature decrease, and we can get to low temperatures where we can take advantage of this for refrigeration.